One of the areas I've been working fairly heavily on in the last few years is generally computing environments to support statistical research and data analysis, and in particular in the context of the R language. Many of you are probably familiar with R. It was originally developed by Rob Gentleman and Wasi Haka at University of Auckland in New Zealand as an implementation of the S language from Bell Labs. S was developed as the tool for the Bell Labs research group to allow them to do the kind of work they do, which involves work and doing data analysis on a wide variety of different kinds of problems, and they need the ability to easily adapt core software tools to different kinds of data, and the S language evolved from that. R has become the main framework for developing new statistical methodology, not the only one, but I'd say the main one. It's pretty rare nowadays for a PhD thesis not to include an R package implementing the ideas that people are putting forward. And that, among other things, has resulted in some 7,000 extension packages available through some of the standard package repositories. The effectiveness of the R language and S comes from a number of features that it incorporates, starting with vectorized arithmetic, like the APL language, and add a constant to a vector in a single operation. A key factor for statistics is data support. Functions are first class, meaning you can have functions argument down to an optimization routine, or have a procedure to return a function that represents a likelihood, for example. These features and the others are all things that make the language powerful and effective, but they also represent challenges in making the implementation efficient. So what I'll talk about is a couple of things that I and some of my colleagues have been working on over the last few years, and I will be working on going forward to try and make improvements in the context of R. So one of the things I've been working a lot is developing a compiler for R that will speed up the basic evaluation. Basic evaluation of a language like R typically involves taking the characters you type for your code, turning them into a parse tree, and then that tree is what the interpreter will walk through to compute values associated with what you're doing. And if you're looking at a loop, it will walk through the body of the loop each time, and that's a lot of overhead associated with it. Low-level languages like C or Fortran typically go through a compilation phase that translates them into machine code, which runs much faster as opposed to the native hardware you're running. An intermediate approach followed by many languages is to translate the parse tree to an sequence of instructions for a very simple machine, but one that's not typically implemented in hardware, but rather implemented by a C program. But because the language is very simple, the C program can be very fast. The language is often referred to as bytecode that you translate into, and the machine that executes the bytecode, because it's not hardware, is referred to as a virtual machine. There are some general purpose virtual machines, like the one from Java, that can be targeted by other languages, but most higher level languages that use this strategy have specialized virtual machines that know things like perform an addition operation. Typically that's done on scalars, but it might require dispatch to the system's object mechanism and so forth. So we follow that approach in R as well. Once you've got translation for this simpler machine, there are other strategies you can follow from there. You can translate actually down the machine code and then run it in the most efficient way. And that's one of the options we're looking at. I'll say a few words later about that. In terms of the way the compiler, which was added to R a couple of years ago, works, you can use it explicitly by you've got a function, you want to compile it, you pass that function on to a CMP fun, get back a compile function and use that. Just similar with a script file. The most common way people tend to use the build compilation is by adding an annotation to your package saying, I want this package to be compiled when it's installed. The third option is to enable a JIT, or just-in-time compilation mode, where each time the interpreter hits a function, it isn't compiled, the That's not yet the default available, but it's a decent chance it will become the default in the next major release, which will be about a year from now. Just a little bit on performance improvements. These are just 4 fairly straightforward examples of heavily scalar code, the type that ideally you won't have to write very often, but sometimes you do, and that's where the compiler makes the most difference. The speed-ups shown here are what's achieved with the version of R that most of you probably have access to. It's the one released last year. They're fairly decent. Some substantial improvements were made in the execution engine, and the version of R that was released just a couple of weeks ago, 3.2, gives us much better speed-ups. It's the final column. There's some work going on right now to explore moving from bytecode to native code and just translating the bytecode directly to native code and moving the virtual machine overhead. It looks like it's getting us another factor of 2 improvement. The main reason to go that direction is to possibly then enable function optimizations that can get much more in some cases. So that's a direction currently being looked at. Right now, we're just doing things by translating to C, run the C compiler, but we'll end up, this looks like a promising group, probably go into something like LLVM for generating the code on the fly, machine on the fly. So that's one direction. Another direction is more, next 2 things we mentioned are motivated by dealing with deal with larger and larger data sets. One of the features that I didn't have on my list but didn't mention is that R provides the illusion that when you write a function and you're working on a piece of data that's been passed to you as an argument, you can modify that data without affecting the original value. It makes it much easier to write code that's robust, eliminates errors that would happen if you potentially change data sets that live somewhere else. The downside is that in the simplest implementation, you have to copy data sets each time you call a function, which is just not viable. You can't do that even with small data sets, but instead, so you have to copy on write or copy on read, and that's what R does. But it has to be a little conservative, and it's right now still being too conservative. Too often with results and slowdowns. So we're looking at ways to improve that. One major effort Michael Lawrence added some code to highly tree-structured data structures only duplicate the parts that have to be copied. It's called channel duplication. This is most relevant for things in the bioconductor project, which is a very big part of the R ecosystem. We're currently looking at some ways of changing the way we detect when copying is needed by using the proper reference counts as the current mechanism. This looks fairly promising as well. Fairly confident this will make it into the next R release. Another direction, when R was first developed maybe 20 years ago, it was designed in such a way that the maximum number of elements a vector could have was the largest signed 32-bit integer, which is about 2 billion, which was more than enough 20 years ago. It's still more than enough for most people, but not everyone. So we tried to, and we have raised that limit. For now, we stuck with a static limit on number of columns, number of rows in a matrix, mainly because of Fortran code we talked to. But the total size is now released. And it's done it in a way that we can do things gradually rather than have to rewrite everything completely. And you can now compute fit linear regression models to nearly 2 billion cases, at least a billion cases, and 1,000 variables. That's doable. It takes a while. It takes a while just because it has to with that bigger problem. It also takes a while because there's some things that we do that make sense in smaller problems that we really shouldn't be doing in bigger ones. For example, calculating the residuals. You're not going to observations. Calculating the full cube component of the QR factors, things like that. So having gotten this ability, one thing that we do is to figure out what should be done differently, algorithmically in terms of better algorithms, maybe parallelized algorithms, other issues that come up. If you run a regression data regression, you decide I didn't really want to do that. I wanted to transform a variable. First, it's going to take 10 minutes to finish. You'd like to be able to interrupt it. That's something that needs to be figured out. So that's another major focus of what we'll be doing. In the spirit of what Kate was talking about, I'm at the moment focusing mostly on multi-core systems rather than GPUs, but some of this could apply in that direction as well. We need to look into ways of taking advantage of multiple cores. Since R is a vectorized language, vector operations naturally can be split over multiple cores in principle. And so we're trying to figure out ways of automatically doing that in practice, keeping in mind that if you parallelize something for too small a vector size, you can actually slow things down because of the overhead. So we're working through using the OpenMP framework, and hopefully some things from this work are going to be integrated in the distant future. The final thing I want to mention very, very briefly is in order to help us and help users figure out where performance bottlenecks are, if there are any, things are running fast enough, you don't worry about this improving things. But if things are too slow and you want to find out where you should put your efforts, profiling is a very valuable tool for that. R has had a sampling-based profiler for a long time. The summary function it has available for looking at the profile data is fairly primitive. So together with Actuarial, we're looking at some improved tools. For example, you can now get various summaries of the performance linked to the source file in which a function was defined. In this case, I'm just showing the lines of the source files that have high percentage of time spent in them. So this is a linear model fit, and about 40% of the time is in the C code that implements the QR-based computation. So that's where a lot of the time is spent, but it's only 40%. All the rest of the time is stuff probably should be doing faster. So that was a useful thing to learn. And we also produce graphs like this that a call graph with the side representing the amount of time spent in each function. So tools like this are going to be put together in a couple packages that will be released in the not too distant future, I hope. Just to wrap up, a number of different topic areas. They're all related to performance. Many of them are related to working on larger data sets. There's synergy in that compilation will allow us to do things like fuse together a bunch of vectorized operations so that we can parallelize as a chunk rather than fine-grained parallelism, which would make things more efficient. As we go forward through this, we're going to have to probably get fairly sophisticated at some points. If you look at the list of people working on R, all of us have statistics PhDs, and we work on it because it's a tool that we really find valuable for our other work. We're not trained in computer science, but we certainly learned a lot about it. It would be nice to start working with some computer scientists, and we're starting that. The challenge is that computer scientists want to do something very interesting that they can publish in a journal, but they don't necessarily have the incentive to keep maintaining it. So for us to bring it into R, we have to have either a commitment to somebody who understands it to work on it, or the ability of people who understand it to train us so we can work on it. It's an interesting challenge faced by things like Python as well. There's lots of research articles on Python in the CS literature, not as much as you would like it's fed, that you might think is fed back into the Python that people use on a everyday basis. But we've got some interesting collaborations going, and it'll be exciting to see what happens in the next